अच्छा, हम ये दो कंपोनेंट अभी पढ़ रहे हैं, इनका डिज़ाइन पढ़ रहे हैं। तो इस डिज़ाइन में हम पहले देखते हैं ये कि जब से बनना चालू हुआ, जब से डाइवर्जन वाटर का चालू हुआ, जो नेचुरल स्ट्रीम्स थी उसको हमने जैसे जैसे डाइवर्ट किया तो इसकी हाइट भी बढ़ती गई। जैसे जैसे हाइट बढ़ती है तो पानी अपस्ट्रीम में ज़्यादा स्टोर होने लगता है और कैनाल का साइज़ भी बड़ा होता है। डिस्चार्ज हम ज़्यादा एरिया को सप्लाई करने लगे। जो कैनाल का एरिया है उसको कमांड एरिया कहते हैं, जिसमें इरिगेशन होता है। मोस्टली इरिगेशन टर्मिनोलॉजी है ये कमांड एरिया। और उसके अलावा भी जो पर्पस थे हमारे ड्रिंकिंग के या कॉमर्शियल इंडस्ट्री का वाटर रिक्वायरमेंट था, उसके लिए पानी को डाइवर्ट किया। तो इस डाइवर्जन के लिए स्ट्रक्चर्स बनने लगे और हम डे ऑन डे बेसिस से इसकी रिक्वायरमेंट बढ़ती गई। तो जो नेचुरल फ्लो है रिवर का, ये एंड अप होता है ओशंस में जाके, और वहाँ पे पानी की यूटिलिटी ख़त्म हो जाती है, क्योंकि ये समुद्र में जाके पानी ब्रैकिश हो जाता है और वो फिर पीने लायक या कृषि योग्य नहीं रह जाता। तो उसको हम क्या करते हैं कि पानी न ये समंदर में जाके मिले उससे पहले ही डाइवर्ट कर लेते हैं, और हम हमारे जो ह्यूमन डेवलपमेंट और जो सिविलाइजेशन के लिए यूज़ होता है, जो हमारा नेशनल ग्रोथ है, उसमें उसको पुट अप करते हैं। तो किसी भी कंट्री का हमने देखा कि कैसे ग्रोथ डिपेंडेंट है ये प्रीवियस लेक्चर्स में। तो अभी हम उस वियर की डिज़ाइन को देख रहे हैं कि वियर कैसे स्टेबल रहे और उसके इंटेंडेड जो एज है या उसकी जो लाइफ स्पान है वहाँ तक वो खड़ा रहे, उसमें प्रॉब्लम नहीं आए और ये डाइवर्ट करता रहे। एक बार एक स्ट्रक्चर हमें प्रॉब्लम देने लगता है तो पूरा जो प्रोजेक्ट है इरिगेशन या ड्रिंकिंग वाटर सप्लाई का, वो पूरा प्रोजेक्ट हमें दिक्कत देने लगता है। तो इस डिज़ाइन में फेलियर को स्टडी किया गया कि जब हम डिज़ाइन हुए इनिशियल 20th सेंचुरी में जो डिज़ाइन किए गए डाइवर्जन के लिए, तो उनमें से कुछ एक वियर्स जो थे वो फेल हुए। तो फेल होने के कारण स्टडी हुए, तो उन कारणों को हम लास्ट टाइम डिस्कस कर रहे थे। मैं अभी आपके साथ फिर से स्लाइड्स शेयर करता हूँ और उसमें हम आगे बढ़ते हैं। आपको स्लाइड दिख रहा है? स्लाइड आपको विजिबल है?
यस सर।
ओके, और मेरा एरो भी दिख रहा है आपको?
हाँ सर।
ओके, तो इसमें इस जो आपके आईएस कोड है उसमें डिज़ाइन, डिफरेंट डिज़ाइन के टिपिकल स्केचेस दिए हुए हैं। आप के साथ मैं शायद शेयर नहीं किया, मैंने डाउनलोड कर रखी है, मैं भूल ही गया, और अभी लेक्चर ख़त्म होने के बाद फिर से शेयर कर लूँगा। उनमें भी ये स्केचेस दिए हुए हैं, आपको मिलेंगे, और डिज़ाइन दिए हुए हैं डिफरेंट कंपोनेंट्स के। जो फॉर्मूले जो हम पढ़ने वाले हैं, ब्लिग्स थियरी या लेंस थियरी या खोसला की जो थियरी है उनको पढ़ने वाले हैं, तो वो सारे उसमें दिया हुआ है, इन स्केचेस के साथ एक्सप्लेनेशन दिया हुआ है। तो लास्ट टाइम हमने ये सारे कंपोनेंट वियर के पढ़े थे। आप यहाँ पे मैंने दिखाया था आपको कि ये क्या कंपोनेंट है और उसका कैसे फेलियर होता है। तो लास्ट टाइम हम इस फ्लोर के बारे में बात कर रहे थे। जो यहाँ फ्लोर बना हुआ है ये काफ़ी मॉडिफाइड फ्लोर है, ये काफ़ी मॉडिफाइड है। इनिशियल स्टेजेस में ऐसे फ्लोर नहीं थे, एक फ्लैट थिकनेस के फ्लोर थे। जब 20th सेंचुरी 1900 अराउंड इन बिगिनिंग में 1910-20 में, तो ये वेरिड थिकनेस के फ्लोर नहीं थे। जो यहाँ पे थिकनेस है, मान लो कि 1 मीटर है, 1.5 मीटर है, तो ये चेंज हो रही है। और यहाँ पे ये डिफरेंट कंपोनेंट्स दिखाए हुए हैं, इतने सारे नहीं थे। इनिशियली केवल फ्लोर बनाया और उसके ऊपर ये स्ट्रक्चर बनाया। तो इसकी फ्लोर की लेंथ फिक्स की गई इनिशियल लेवल पे, और कि कितनी होनी चाहिए, और उस हिसाब से इसका जो अपलिफ्ट प्रेशर हम लास्ट टाइम डिस्कस कर रहे थे कि अपलिफ्ट प्रेशर कंपोनेंट होता है, उसके हिसाब से। तो इसके दो टाइप के फेलियर होते हैं। एक होता है कि जो सरफेस फ्लो हो रहा है, यहाँ से जो पानी आ रहा है और इसके ऊपर स्ट्राइक कर रहा है, और स्ट्राइक करने के बाद जो एक्सेस वाटर है वो डाउन स्ट्रीम में गिरता है और गिरने के बाद चला जाता है। तो ये सरफेस फ्लो हुआ। और सब सरफेस फ्लो कौन सा हुआ? जो यहाँ से सीपेज होता है पानी का, जो इसके अप फ्रंट जो रिवर बेड है यहाँ तक हमने प्रोटेक्शन कर रखा है। इसके आगे यहाँ देखा जाए तो पूरा जो रिवर है उसका केवल रिवर बेड है एंड दैट इज परमिएबल। सो ये जो प्रॉब्लम आ रही थी हमें रिवर के जो स्ट्रेचेस अलुवियल रीजन्स में हैं, अलुवियल स्ट्रेचेस में हैं, जो थर्ड स्टेज होती है रिवर की, फर्स्ट और सेकंड मोस्टली माउंटेनियस रीजन में होती है। जब ये रिवर बनती है तो वहाँ पे माउंटेनियस या हिली रीजन होता है और ये बहुत ही नैरो रीजन में चलती है, वाइड नहीं हो जाती। और वहाँ पे जो नीचे फाउंडेशन होती है वो काफ़ी स्ट्रॉन्ग इम्परवियस होती है और वहाँ पे इरिगेशन की इतनी ज़्यादा रिक्वायरमेंट भी नहीं होती क्योंकि इरिगेबल लैंड ही नहीं होती, वहाँ पे कम होती है। लेकिन फिर भी वहाँ पे यदि ये ऐसा बनाया जाए तो कम दिक्कत देता है। ज़्यादा प्रॉब्लम हमें पानी की कहाँ ज़रूरत होती है? जहाँ इरिगेबल लैंड हो, जहाँ एग्रीकल्चरल लैंड हो, जहाँ एग्रीकल्चरल होता हो। तो मान लो कि हम यमुना और गंगा की बात करें इंडिया में, ऊपर से जब नीचे उतरती है तो अलुवियल कहाँ आती है? उत्तराखंड से नीचे आते आते उत्तराखंड, यूपी, बिहार, इन एरिया में ये प्लेन लैंड है, अलुवियल सोइल है। इवन गुजरात का हम कंसीडर करें तो इट्स नॉट दैट स्ट्रॉन्ग फाउंडेशन। तो इन रीजन्स में जब हम वियर बना के डाइवर्ट पानी करके एग्रीकल्चरल एक्टिविटी को प्रमोट कर रहे हैं तो वहाँ पे इस टाइप के वियर को क्या क्या प्रॉब्लम आ सकती है? तो मोस्टली जो वियर का प्रॉब्लम है वो अलुवियल स्ट्रेचेस, जो रिवर की थर्ड स्टेज होती है, और फाइनल स्टेज जो फोर्थ स्टेज है वो डेल्टाइक होती है। जैसे मैंने लास्ट टाइम मेरे ख्याल से वो मैंने दूसरे वाले लेक्चर में लिया था, जो हमारा जियो इन्फॉर्मेटिक्स का लेक्चर है, उसमें जो डेल्टाइक रीजन है वो फोर्थ स्टेज होता है। जैसे भरूच से आगे जाके जो हमारी नर्मदा रिवर गिर जाती है तो वहाँ ये स्प्लिट हो जाती है रिवर बहुत सारे स्ट्रीम्स में एंड देन इट जॉइन दी अरेबियन सी। सो दैट इज डेल्टाइक रीजन। उसमें ये स्ट्रक्चर क्रिएट करना बहुत ही एक डिफिकल्ट है और वहाँ पे जनरली करते भी नहीं है। तो लेकिन अलुवियल रेंज भी काफ़ी किलोमीटर्स में रहती है, मतलब हंड्रेड्स ऑफ किलोमीटर्स। सम ऑफ द रिवर्स आर रनिंग इन like 500,000-700,000 kilometers in alluvial stretch, and we need to check the flow to divert it by constructing dams or weirs or barrages. So these hydraulic civil engineering structures need a kind of stability, and to bring stability we study the forces. So here forces are of two types. One is the surface water flowing here, striking directly onto the structure and falling onto the other side downstream of it and eroding the floor or the river bed onto this side. So surface flow से जो इसका फेलियर होगा, so वो एक टाइप का फेलियर है। सेकेंड फेलियर मैं डिस्कस कर रहा हूँ आपके साथ, जो बहुत ज़्यादा अननोन है, जो इनविजिबल है, जो फोर्सेस एग्जर्ट तो करता है, फोर्स इस स्ट्रक्चर पे एग्जर्ट तो करता है, लेकिन हमें पता ही नहीं है कि किस टाइप के फोर्स और कैसे एग्जर्ट करता है। तो इसकी स्टडी बहुत ही टिपिकल थी, बहुत ही मायने रखती थी कि कैसे इसको स्टडी किया जाए। सीपेज जो नीचे जा रहा है वो कैसे हमारे स्ट्रक्चर को अनस्टेबल कर रहा है। हम हमारी जो बिल्डिंग्स, हाई राइज बिल्डिंग्स बनाते हैं उसमें भी हम जो फाउंडेशन डिजाइन करते हैं, स्पेशली जो हम फाउंडेशन डिजाइन करते हैं स्पेशली, तो क्या होता है कि इसमें उस एरिया का जो, जैसे वेभाव टावर अर्थक्वेक में गिर गया था, यहाँ पे एक मानसी टावर गिर गया था, तो ये गिरने की वजह भी ढूंढी गई। तो इसमें कहीं ना कहीं जो कंट्रीब्यूशन था लूज सोइल का था, सोइल की कैपेसिटी का था। वैसे ही यहाँ पे सोइल की जो इम्परवियस अलुवियल सोइल है, इसकी कैपेसिटी नहीं होती इसको होल्ड करने की, और सेकेंडरी जो फोर्स है वाटर का वो इसको इम्बैलेंस कर देता है स्ट्रक्चर को। देन स्ट्रक्चर विल crumble down into the hollow space created because of the seepage onto this side. Now we are studying that how it fails by two things. One is the direct flow here, that water is flowing and coming out onto this side. Then I explained to you last time that it has a kind of head. So this is head of water upstream of the structure. You can assume it as H. And this head is having energy, kind of energy, you know, any pulling up or any kind of piling up would exert the force onto it. तो हम जब प्रेशर को करते हैं, प्रेशर डिफाइन करते हैं, तो प्रेशर फोर्स में कैसे कन्वर्ट करते हैं? विल मल्टीप्लाई pressure by area to get the force being exerted on the structure. Likewise, एनर्जी को कैसे डिफाइन करें हम, एनर्जी को फोर्स में कैसे डिफाइन करें? तो वो एनर्जी को इफ यू मल्टीप्लाई बाय वॉल्यूम, देन यू विल गेट द फोर्स एक्सर्टेड ऑन टू द स्ट्रक्चर. सो ये जो हेड है, इससे इट्स अ काइंड ऑफ एनर्जी. आप टोटल एनर्जी लाइन ड्रॉ करते हो जब आप ओपन स्ट्रक्चर्स, ओपन जो चैनल फ्लो पढ़ते हो, तो उसमें आपने टोटल एनर्जी लाइन ड्रॉ किया था. वो energy is one kind of force being exerted onto the infrastructure, civil infrastructure we create in and around that flow. So that flow is causing the loss of strength of this soil, loss in the strength of this floor, loss in the strength of this structure, and that leads to a failure. How it happens we'll discuss further, and let's see few more blocks so that you could understand the Bligh's and Khoslas theory in totality. So here this is upstream protection done beyond the floor. This is concrete floor, this is dumping of concrete blocks, and then the talus is nothing but the rock boulders kind of thing. They are kept so that erosion, the scouring of the water because of the surface flow should not take place. So this is to stop the scouring in the upstream side, and this is the concrete block here, and here the again talus blocks or the rock boulders are kept laid down in rows and with the core walls and to stop the scouring onto the downstream side of the floor. And these are provided also with an inverted filter. Filter is like strainer we use for tea, and this water is going up, so we want that only water is oozing out of here, not the soil particles. So we provide a kind of filter material here. This is a kind of like these are big boulders here, and these are the smaller pebbles laid down here. So water will come out of between these concrete blocks and will not allow the soil material which is here down the floor come out onto this side. So these are the production for scouring of the because of the surface flow. So there are basically four types of failure defined by these technocrats, engineers while designing this structure. Likewise, if you look at this structure, this is barrage, and here also you will find that this is floor, which is not having kind of a common flat thickness throughout, but the thickness is varied. And why varied, we'll look at that why this varied thickness is provided. And again here the concrete blocks are laid, and then inverted filter are provided, and apron is mentioned here onto this side. This is apron is like this here, blocks, terrace material which is laid in the layers to protect the scouring, to protect the bed of the river from scouring in the upstream and downstream. So similar kind of protection is given here. The sheet pile is of the concrete material provided onto the upstream. It can be provided metallic sheet pile like this. Here it is provided one at the front and the second at the downstream of the floor. The depth of the sheet pile is more compared to upstream here. This is just for information so that you could understand the theory which we are going to discuss. Likewise here this concrete upstream and downstream pile is provided. This has been inserted into the soil foundation, say 10 feet or 15 feet deep, to protect from the uplift pressure which we have discussed last time. For the sake of your knowledge, I again explained that uplift pressure is nothing but the pressure applied by the the pressure applied by the seeping water. Water is seeping through this soil media, and similarly, while seeping, it is being held in saturation. Some water always there throughout this soil formation over here, and it keep exerting the pressure, and that pressure is called the uplift pressure. So to protect this floor from the uplift pressure, we have to provide this thickness to counterbalance the uplift pressure, and the depth or the thickness of this floor is dependent mostly on to the amount of the uplift pressure being exerted by the water in the soil. So let's have a look upon the next few topics. This we have already. Should I clear again once again this the kind of structure here? This is main structure of the weir. This is shutter provided. Sometimes sorry, this shutter we can lower it down in the groove provided in the weir, and mostly it is kept to hold the water. And here this gates are provided in case of barrage through a mechanical arrangement. This dotted line here represents the cables through which it is being lowered. It's a case of Vasana barrage you can consider, and it is lowered to raise the height of the water. So this is here the pond level. This is a permanent structure. Here the gates can be lowered down, and the HFL could be achieved high flood level up to this. When we do not need, we open, we take these gates up, and water will come out of this area and go to the downstream of the river. Similarly, the excess water here will come from the top of it. So in case of flood, say in case of the storm events, this water is getting pulled up here and will submerge the area. Is one of the you discussing that there would be a kind of submergence upstream. Definitely there must be submergence because of this afflux created. Afflux is this excess water here. Otherwise the depth of rivers was something like here, and this additional depth which has been added because of this structure is called the afflux. Depth of this water which is being stored upstream of the structure is called afflux. You could send me the question in the chat box if you are not comfortable with my explanation at any level. I skip this slide. I have already explained to you. Now coming to the weir and different types of weir, I'm not going to take them in detail. We have already discussion on this. Vertical drop weir, rock fill, and then this. This one I have shown to you is the vertical drop type of structure. What is written here, last bullet, vertical drop weirs were quite common in early diversion headworks, but these are now becoming more or less obsolete. So they are mostly not being used, but the basic fundamental theory remains the same, which has been conducted by the technocrats on these structures. And now the secondary type of structure is this type of structure, wherein we provide here the shutter, and this is a weir wall, and then core material is dumped, and in between rock is filled. So one of the Okhla weir in Yamuna at Delhi area, you will find this kind of structure. They take large amount of space and material to be dumped and not in again use. So mostly nowadays sloping or glacis type of weirs are provided, but whatever you do when we study, the design remains almost similar to all. So what is a glacis or sloping weir? This is a kind of concrete weir. I'll show you the sketch. Last time also shown you one sketch, and the design is almost same. Here the compacted formation is done, and we lay the concrete floor like this, So what happens that in front there is this kind of slope provided here, and then there is a flat surface. So this gives us height. This represents the bed level of the river, and here we achieve the height of the weir, and we achieve certain height through the by providing a shutter on the crest of this weir. So this is the top of the pond level being stored, and on the other side a sloping floor, and this floor is sloping. There in previous the vertical drop weir, it was horizontal floor. So now we are laying what downstream a sloping or a glacis floor, and that's why this this kind of weir are called glacis. Glacis means sloping, the other meaning of this. So and down this is the compacted material formation done, and it is resting, and then the floor is taken to the bed level again, and at the end we are providing similar protection to the concrete blocks and the boulders onto the both side upstream and downstream. The main advantage of this glacis type of weir is that when there is excess flow taking place in in case of flooding situation or in monsoon, that excess water is going downside, then there is a good depth of water up above it, and that whole water, the excess water, falls onto this slope, and there is a formation of hydraulic jump. So formation of hydraulic jump is considered in favor of design, because formation of hydraulic jump facilitate the dissipation of energy. We are looking for the formation of hydraulic jump to dissipate the energy onto this side, because this energy, excess energy, when this water is getting pulled up, getting altitude or height here, having lot of energy, it will spoil the downstream floor or the downstream bed of the river. To protect that, we need to dissipate, we need to destroy the extra energy of the water, and water should come to the normal flow with the normal depth. The depth of flow should not be more than the critical depth of the water, and if the flow is more than critical, then it will erode the bed of the river that we have seen in the open channel flow. So this kind of glacis type of weir facilitate formation of hydraulic jump onto this downstream side of the glacis floor somewhere here, and it facilitate the dissipation of energy. This explanation. Now coming to the main thing which we were discussing. These failure would lead to the three theories of design. That basically you could read what has been written onto the screen. So two types of failure are defined: subsurface and surface flow failures. And then to subsurface failure, there are two types of. One is the piping because of the exit gradient. Exit gradient I defined last time, that the total head divided by the total length of the floor will give you the gradient which exists throughout the length of the floor, and the remaining gradient which is at the exit when that flow ends. That floor ends there, if it is more than the critical gradient, then if exit gradient is more than the critical gradient. Critical gradient means what? The critical gradient is gradient above which, if there is any head or energy available, it will bubble the soil, it will boil the soil, and soil particle will start moving in the seeping water and will come out, and piping action will start from the downstream. I will show you in the figure next few slides. And the second is rupture or breakage of the floor because of the uplift. So that I have explained to you. I show you something. This is just very good point mentioned, which we have discussed. You could have a look onto these points. I explain onto the sketch drawn. These are the failure due to the surface flow. One is by the suction of the hydraulic jump which is formed, and the second is because of the scouring. Scouring I have explained you in terms of the concrete blocks and in terms of the terrace or the boulders which we lay down to protect the bed because of the high velocities of the flooding water in monsoon season. So that is scouring, and the suction is I read it out. In the glacis type of weir, a hydraulic jump is formed onto the downstream glacis. In this case, the water surface profile. In this case, the water surface profile in the hydraulic jump trough is much lower than the subsoil hydraulic gradient line. Hydraulic gradient line, HGL. The total energy line, TEL, you have seen in the open channel flow. Here we are studying hydraulic gradient line, that is H by L. So that hydraulic gradient line is higher in terms of the subsurface profile of the hydraulic jump. So in that case, there is lot of pressure. Therefore, uplift pressure occurs on the glacis. Glacis means the downstream flow. This uplift pressure is known as the suction pressure. In that case, uplift pressure get converted into, we consider that as a suction pressure, because the profile of the hydraulic jump is lower than HCl. So that creates kind of suction on the glacis, and if thickness of the floor is not adequate, then rupture, means cracks, will develop onto the glacis, and that may lead to failure. So these are the two surface flow failure of the Now, with the help of these failure concept, the failure, we assume that surface failure and subsurface failure. So these has been studied by these technocrats, and they have given kind of understanding that how we should design the floor. So design of floor was basically to find out the length of the floor. That length of the floor, the LT means the total length of the floor, total length of the floor, this LT. And then also the thickness of the floor here, that what thickness should be provided to protect it from the uplift. So that is what is the theory about. So this was given in 1910, and what he assumed, Bligh, B-L-I-G-H, Bligh, assumed that percolating water creeps along the contact surface of the base profile of the structure with subsoil. What he assumed, when water seeps here on upstream side, this is where you assume this line give you is where this is H is the head created upstream of it, total head created. So this head means the energy, and energy will lead to seepage of water percolating through this soil media, which is not protected by the concrete blocks or anything. So this whole area upfront of this protection will allow the water to enter into the soil mass, soil formation, and it will go into this soil and will come out onto the other side. So what he has assumed by that time means during the 1910, he assumed that water starts seeping here at this junction of the floor and soil where no protection is there, and it creeps like this, come down, and then again seeping water will adhere to the rear side of this pile and will come here, and then it will flow, the seepage flow will take place just adhering to the bottom of the floor, and it will come down if there is any intermediate pile inserted, provided, and again it will go up, and again it will go horizontal like this, and here go down and will go up and will come out. So the total length this water will travel in the flow line. When we understand in fluid mechanics the flow is taking place in terms of flow line. So flow line is this much, the total length of flow line is this much, and exactly he has assumed this as the seeping water is adhering to the surface, bottom surface of the floor as well as both sides of the pile, and it will come out somewhere here. So he has just assumed the flow in that way, and total length for that purpose he has calculated the total length of the flow that he called creep length, C-R-E-E-P, creep length, LT, as 2 times D1. D1 is the depth of pile here. So 2 times the flow takes place 2 times, one while coming down and the other while going up. But it takes only LU is this upstream is this much length only, and this is only one length the flow travels. So one only, and then again 2 times the D3 pile is taking place 2 times. Then the downstream length of the floor is taken this one single time, and then the last D2 pile twice of that flow taking place. So this is LT, the creep length, and this HS, the head available. So this head should be destroyed while traveling, the flow traveling in this total creep length. So what he assumed that HS, you look at this diagram, that HS is the height or the head, which is the upstream minus downstream head. If the downstream there is any water, then we deduct that also from the upstream head of the water, and HS is taken as the net head net head to be destroyed in total length LT, and when it come out here at this point, then this head becomes 0. And when head becomes 0, then your gradient, hydraulic gradient I is h by L. If h is 0, then I becomes 0. So he assumed that this LT should be taken in such a way that it destroys this HS total to the 0 level. So he has no concept of the permissible gradient at the exit, as it would be clear in the Khosla's theory that he has assumed that for different soil there is a permissible gradient, hydraulic gradient, and we call it as critical gradient. But here he has not taken that concept into consideration, and he brought it to 0, and for that 0 value he has taken this LT. Suppose this HS is not coming to 0 here, then what he has done, that he has inserted more piles, like he has inserted 1, 2, 3 in this sketch. He may be inserting few more piles to bring this head, as it is more and more. If we are going a weir with more depth or more height here, then we need more length of this. So that is what is the theory of Bligh, that we calculate LT, total creep length. This LT is nothing but the creep length of the Bligh's theory, and HS is the net head, and it need to be destroyed onto the exit of the seepage. So that is what is the theory of Bligh. So very simple, and many times there is a question of 3-4 marks in the university examination. So very simple, that you calculate net head and you calculate the creep length and find out the hydraulic gradient for which you could design. So what is this? This last bullet I read that the head loss is proportional to the creep distance traveled. This head loss is proportional, means linearly proportional. This is not like reducing very sharply. So we'll see this, the Khosla's theory, this linear loss of head is also challenged by the Khosla. So we'll look at this line, that why this is not a straight line and why this is a curvilinear line. So that we'll see in the next theory. Now here, to calculate the total creep length, what he has given, that the hydraulic gradient is inverse. This is hydraulic gradient HS by LTI. I have defined you. I defined just before onto that slide that this is the hydraulic gradient here, and the hydraulic gradient is inverse of Bligh's creep coefficient. He has given some certain creep coefficient, Bligh's creep coefficient C, which varies from 10 to 18. So if I assume that this is I, then this I is what? Hydraulic gradient is inverse of Bligh's creep coefficient C. So 1 upon C is equal to HS upon LT. HS upon LT. You can assume in that way. So 10 to 18. So LT in that case would come out as CHS. So whatever is the net head, you multiply by this Bligh's creep coefficient 10 to 18. This 10 to 18 depends upon different soil material, bed material. So for a good soil, say coarse soil, this may be like 15, 16. You can take, and fine sand, which can bubble out, boil out easily. We have to take lower values of the bed material in that case. So LT, if suppose this is 18, or for calculation I say take 20 and head is 10 meter, then the length of the floor including the pile length, it should be 20 times 10 is equal to 200 meters, something like that. So this calculation of LT comes out as C.HS. The last bullet, the uplift pressure at any point can be determined by Bligh's theory and then required thickness to counteract it. So what is the uplift pressure? He assumed that there is a linear loss of head. So at the beginning, the uplift pressure is this. When we study the forces, the uplift pressure is some factor. If you look at the IS code, then there is a factor also defined which is very near to 1. So almost this ordinate you can take the beginning of the uplift pressure and at the end 0. But if it is not 0, then we have to look into that whether it is critical within the critical range or not. All other point here it is reducing. So there is no need of providing the uniform thickness throughout. Even because of this theory, there is lot of uplift here on the upfront here and lesser uplift there onto the end. So if we do not provide this much thickness, uniform thickness throughout, then it's okay. But he assumed a constant thickness throughout, and that was also a kind of limitation of that theory. You read out this, many of things we have already gone through. What it states that while onto this, now we are leading to the next theory. I will cover only 2 today. I'll take 2 more slides beyond this. Khosla's theory I'll take up in the next lecture. And after the Bligh, there is lens theory. And to arrive at the lens theory, we have to look at the limitation of Bligh's theory. So what happened that he assumed that creep length is this, water flows adhering to this. And he assumed that the upstream, this front and the rear portion of the pile are equally effective in counteracting the energy here of the seeping water, but this was not true. Then he assumed that each and every pile are equally effective. Here the upstream pile, here the downstream pile, and here the intermediate pile. He assumed that the all piles are having equal effectiveness. As well, the upstream side and the rear side of the pile are also effective. But there were troubles after this Bligh's theory. There were many structures created in the northern India to divert the water for water diversion, and many of them failed because of the rupture into this floor. And once there is a rupture or crack in this floor, means the total length has been reduced to this point. So LTA has been reduced and more energy concentration takes place, and there is a kind of complete failure of the structure. This whole structure will subside into this mass foundation, which has been hollowed because of the removal of the soil particle onto the other side. So this effectiveness has been studied by the Lane. And what he has given that all the piles are not effective equally. So that was the important thing has been demonstrated by the lens. So I'll take you to that slide. The limitations. Which I have just emphasized. The fourth one is that the downstream pile, he has not emphasized the importance, whereas in the third theory given by the Khosla, they have come out with that if you do not provide the downstream pile, then the design is incomplete, and without that to control the exit gradient is impossible. So this limitation has been added afterwards. So let's look at the lens theory. Now look at this lens theory. In that, this gentleman, after say almost 15-20 years of the Bligh, after 1910, so in almost 1930, he has proposed this after studying so many structures designed by the Bligh's theory, and then suggested this kind of creep length. He has given a kind of correction in calculation of creep length, the total length of creep, and that is how that the file D1 LU, that then this 3D3 and 3D2. Earlier we has taken 2D1. So what he says that horizontal creep length is not effective. In this lane has emphasized that the vertical creeps were more effective compared to the horizontal creep. This L is the creep along the floor, beneath the floor. This is upstream of the floor, this is downstream of the floor, and these are the three piles which we have seen in the previous slide. So there we have taken twice the D1 because of the front and the rear portion of the pile we have considered. Here he says that the theory says that the vertical creeps are more effective in tackling the energy of the seeping water, and we should multiply thrice as compared to this in totaling the length of the creep. So total length he has assumed like this. So this is a kind of improvement in the Bligh's theory, and with this theory many structures also been designed, and also he has given that modified the coefficient C, creep coefficient of the Bligh. So there was certain differentiation between the creep coefficient by lane also. So more or less theory was same, only he has changed the weights to different things and proposed a modified Bligh's theory. So many times it is called as lens theory. Now this is gentleman Khosala's theory. I won't take it, but this definitely would help you understand the basic soil mechanics, the flow in slow soil formation, and then basic design, which is still a very important parameter in designing the diversion headworks and mostly being used. Even our IS codes recommend the use and explains also the Khosala's theory. Khosala's theory run into many books, but here we will have a very concise look of this Khosala's theory, and that how the Khosala been explained the water seeping through the soil formation, because this method also used in design of the non-gravity dams, or you could say the earthen dams, which we create to hold the water, like Kakrapar, Ukai Kakrapar dam is a earthen. Then the Dharoi dam in Himatnagar area on Sabarmati is a kind of this earthen dam. And these dams, if this kind of theory does not exist, then difficult to design. So this design is really important. We'll understand nitty-gritty of Khosala's theory in next lecture to overcome with the failure of this Bligh's theory to sustain or to retain the structure for longer duration on flowing flow. Okay, I stop and I'll come back. You could ask me certain points which I could not really explain in a better manner. So your questions will give more insight into understanding. I stop presenting my thing and I'm coming directly to you. So you could open up your microphone and ask the ambiguity if there is any in understanding. You can open your video and audio and ask the question. There is no communication from your side. Please एनी रबिश क्वेश्चन, जो कुछ भी ऐसा लग रहा हो आपको कि काम का समझ में नहीं आ रहा, बहुत इम्पोर्टेंट है डिज़ाइन के लिए। जब तक आप हम फोर्सेस को नहीं समझेंगे कि हमारी स्ट्रक्चर, जो सिविल स्ट्रक्चर्स हैं, उन पे फोर्स कैसे लगते हैं, तो उन फोर्स को एनालाइज कैसे करेंगे हम, और उन फोर्सेस को नहीं समझेंगे तो हम डिज़ाइन कैसे करेंगे। हम ओवर एस्टिमेट करेंगे फोर्सेस का तो कंक्रीट ज़्यादा जाएगी, हम अंडर एस्टिमेट करेंगे तो स्ट्रक्चर फेल हो जाएगा, ओवर एस्टिमेट में अनइकोनॉमिकल हो जाएगा, प्रोजेक्ट आपका मंजूर नहीं होगा। तो हमें परफेक्ट डिज़ाइन चाहिए, एफिशिएंट डिज़ाइन चाहिए, ऐसा